Tries are another kind of trees, but they're not binary trees. So each child can have several nodes. The name trie actually comes from retrieval. Some people say trie, others call it trees. The other names for tries are digital, radix, or prefix trees. So as I told you earlier, we use tries to implement auto-completion. For example, when you type a search query on Google, you see Google quickly suggesting a few phrases that start with what you have typed. Now, I'm not sure if they have implemented this using tries, but auto-completion is one of the key applications of tries. Now you might ask, why not use an array of strings and return the items that start with a search query? For two reasons. The first reason is that if you have a large number of words or search queries, this array is going to waste a lot of space because a lot of words have the same prefix. For example, pick, picky, pickle, picture, picnic all start with pick. That is the prefix. The other reason is that looking up words that start with a prefix using arrays is relatively slow. We have to go through every word and check to see if the word starts with our prefix. Now, there are ways we can optimize this, but overall, arrays are not ideal for solving this problem. That's where we use tries. Tries allow us to store thousands or even millions of words in minimal space and provide super fast lookups. So in this try, we have a few words, and I guess you can already see them. We have bag, boy, and cat. Now, the interesting thing is that both bag and boy share the same prefix, that is B, and we have stored it in a single place. Unlike arrays, we are not duplicating characters in this structure. Similarly, if you want to store the word baggage in this try, we just need to extend the bag branch. Both bag and baggage share the same prefix. Now, in this example, we have a tiny try, but as you can imagine, each node in this try can have several children, as many as the letters in the English language. So in English, we have 26 letters, and that means each node can have up to 26 children, okay? Also, the root node is always null or an empty character because English words can start with any of the 26 letters. We cannot have 26 roots in a tree. Our trees always have one root. So we treat this root as an empty root and use its children to indicate the beginning of different words, okay? Now, let's say we want to look up a word like bag in this try. What is the time complexity of this operation? We start from the root node. Does this node have B as a child? Sure it does, so we go to this child. Does this node have a child for A? Sure it does, so we go to this node and repeat. Does this node have a child for G? Yes, it does, and our search is complete. Now, what if our try had a million words or nodes in it? Looking up bag would still take the same amount of time. We need 3 comparisons to find this word. So the time complexity of this operation is O of L, where L is the length of the word we're searching for. Technically, this is constant time, but it's not necessarily O of 1 because the cost is dependent on the length of the word we're looking up. It can vary from one word to another, but it doesn't depend on the number of nodes in this try. If the longest word in this try is 20 characters long, the time complexity of the search operation is O of 20 in the worst case scenario. Now, adding a word to this try also runs in O of L. For each letter in a given word, we have to walk down our tree. If the current character doesn't exist, we add it to our tree. The number of operations involved here is equal to the number of characters in the word we are inserting. So, O of L. By the same token, removing a word also runs in O of L. So that's how tries work. Now, before jumping into coding, let's do a quick exercise.